a few years ago.
I think I know him.
Listo, estamos en vivo.
Sí, gracias. Buenas tardes, vamos a dar unos minutos antes de comenzar. What was the name of the student?
Ricardo Jimenez Martinez.
Ricardo Martinez, yes.
He did a super job in our group. Really, really excellent.
Do you know where he ended up?
He's now actually at a small company in the Boulder area building kind of a version of our magnetometer technology.
Uh-huh. So if you don't mind, I'm going to do the presentation in Spanish first, and then I'll give final words in English.
No problem.
Ok, bueno, vamos a comenzar. Buenas tardes a todos. Gracias por su presencia. Es para mí un placer presentar al doctor John Kitching, el doctor que es nuestro conferencista del día de hoy. El doctor Kitching recibió su doctorado en Física Aplicada de Caltech, del Instituto Tecnológico de California, en 1995, y es el fundador y líder de la división del grupo de dispositivos atómicos e instrumentación en el Instituto Nacional de Ciencia y Tecnología, el NIST, que es donde él trabaja actualmente entre un grupo entre NIST en Boulder, en la división de tiempo y frecuencia. Su grupo y él mismo han sido los pioneros en el desarrollo de relojes atómicos de tamaño de chip desde el año 2000 y a la fecha continúa desarrollando e investigando dispositivos muy, muy compactos, como los van a ver ahorita, con un consumo de energía extremadamente bajo. Desde hace mucho tiempo que tenía muchas ganas de escuchar el trabajo del Dr. Kitching, así que me da mucho gusto que haya aceptado nuestra invitación. I have been wanting to hear about your work, and so for a long time now, so I'm really, really happy that you accepted our invitation. So please welcome. Los dejo entonces con el Dr. Kitching.
Great. Well, thank you very much, Eduardo, for the nice introduction and also for the invitation to speak with you today. I hope that you find this presentation interesting, and let me just share my slides here. Okay. All right, is that good?
Yes, we can see them.
Perfect. Okay. So yeah, so what I'd like to tell you about today is some work that our group has been doing over about the last 20 years, focused on making very small instruments based on atomic spectroscopy. And you'll see that the work that we're doing combines elements of precision spectroscopy with silicon micromachining techniques, and also with advanced photonic systems to build devices that are really unique in their combination of precision and also size, weight, power, and cost. So this is a slide here that shows various types of atomic clocks, maybe, or clocks in general, actually. You're probably, all of you, familiar with, the quartz oscillators that are in your wristwatch, and you can get, more precise versions of those that are more stable. And at the other end of the spectrum are atomic standards. This is a picture of an optical atomic clock, one of the best atomic clocks in the world. And this can measure time to an accuracy of 10 to the minus 18, compared to wristwatches, which can measure time to about 10 to the minus 5. So this basically means that, over one day, a wristwatch might lose on the order of 1 second, whereas over the order of one day here, this would lose less than 1 picosecond. And so these atomic clocks are really the most precise instruments right now for measuring time. In fact, for measuring any physical quantity, time is the most accurately measured physical quantity. And in between these two kind of ends, there's a variety of different clocks that fulfill different application spaces. This is a picture of a microwave clock, one of the primary standards here in the United States. This is a commercial atomic beam clock that is used in telecommunications. And then there are these sort of handheld clocks that are used, were developed mostly for cell phone systems to maintain synchronization of the cell phone network. And as I mentioned, there's lots of different ways in which these clocks are important. The very inexpensive versions go into consumer electronics that only need timing at the sort of millisecond or a few second level. Cell phone base stations, as I mentioned, need timing at roughly 10 microseconds, and that's where these clocks are important. Optical fiber telecommunications is, of course, a much faster communication system, and it needs something like 100 nanoseconds of timing. And if you're going to do satellite-based navigation, for example, using the global positioning system, light travels about 1 foot in 1 nanosecond. And so you need to have sort of nanosecond level timing to maintain, your location to within a few meters. Okay, so I realize that many of you are not atomic physicists, and so I wanted to give you just a very, very brief introduction to atomic physics. This is atomic physics in one slide. We work mostly with atoms in the vapor phase. And in particular, we work with alkali atoms, which are atoms that are in the first column of the periodic table. And these atoms have a single valence electron, okay? So what that basically means is the atom structure is shown here. There's a nucleus, of course, that is positively charged. Then there are some number of filled electron shells. And finally, there is one valence electron that is sitting in the outermost shell. And of course, that depends on how far down the periodic table you want to go. Now, the key properties of these atoms that are important here is that both the nucleus and the electron have both angular momentum, basically spin, and an associated magnetic moment. And so what that means basically is these atoms are basically composed of sort of two dynamic particles or systems, one the nucleus and one the electron, and the magnetic moments of these can interact. So if I have my atom, so here is a little cartoon picture of this here, where I'm showing you the spin of the nucleus and the spin of the electron. These are two bar magnets, for example, and you know that the orientation of two bar magnets with respect to each other changes the energy, right? It takes energy to align a north pole with a north pole, and that's the same in an atomic system. So in an atom, in this particular state, for example, it will sit here in some energy level that is, of course, quantized because of quantum mechanics. And there's different ways now that I can interact. I can have electromagnetic fields interact with this atom. So one way is I can shine a laser on the atom, and that will essentially promote the electron into some higher electronic orbital. And the energy involved there takes about 1 electron volt, or in the frequency domain, it takes about 10 to the 15 hertz. Okay, so this is optical frequencies. And that's, of course, why we use lasers to excite these types of transitions between the atoms. Now, I can also shine a microwave field on the atoms, and the energy that the atom gains in reorienting, for example, the electron spin compared to the nuclear spin is on the order of a microelectron volt, or on the order of 1 gigahertz. So if I shine a microwave field on this atom, and I make it resonant with this transition energy here, then I can flip the electron spin with respect to the nuclear spin. Now, as I mentioned, the atom has a higher energy because now the two spins are aligned, the north poles of the magnets are aligned. And so now I can drive transitions between these microwave energy levels in the atomic system. And then finally, if I put this atom in a magnetic field and I look at one particular spin orientation, then I can drive a precession of the atom atomic spins about the magnetic field. And so this is known as Larmor precession, or Zeeman splitting in atoms. And it basically means that when you apply a magnetic field, now the energy separation between these different levels here is on the order of 1 megahertz for a 1 Gauss field. This is just the G factor of the electron. It's about 1.6 megahertz per Gauss, right, is the G factor for hydrogen. So, and other atoms such as potassium, rubidium, cesium have different gyromagnetic ratios, but they're all sort of around this number here of about 1 megahertz in a 1 Gauss field. And you'll see that in the instruments that I describe, we use actually all versions of this, all three of these types of spectroscopy to make the instruments work. Okay, so why do we want to use atoms in instruments like clocks or magnetic sensors? And there's, I would say, 3 main reasons. First of all, because atoms can be made in very, very isolated from the environment, then you can generate very long coherence times. That is, because the atom doesn't have much interaction with, for example, other atoms that would happen, for example, in the solid state. If the atom is just flying ballistically, for example, in a vapor cell, then it means that you can have very long coherence times. And when you set the atom oscillating, for example, in a superposition of these energy levels, it will oscillate for a long time. And you can obtain Q factors of with optical standards approaching 10 to the 15 or even above. And so that's one reason. The other reason is that the energy levels of these systems, this is a very simple, well-defined quantum system, and every rubidium atom or every cesium atom is exactly the same as every other cesium atom. And what that means then is that the energy levels in the atom are all defined by fundamental atomic constants. So here's an example. This is just the Hamiltonian having to do with an atom atomic spin interacting with a magnetic field. And so there's the quantum number of the atom, the spin, and there's the magnetic field. And then there's this coefficient mu here. Actually, I'm just going to make this laser pointer for a second here. Laser pointer. Okay, there we go. There's this factor G, mu out front, which is essentially the dipole moment of the atom. And if you look at this constant here, it's basically a G factor, which is a fundamental constant of nature as far as we know. And then you can see there's the charge on the electron, Planck's constant, and the mass of the electron. And what that means then is that the energy levels here are all defined by fundamental constants of nature. And so every cesium atom, or every rubidium atom, or every hydrogen atom has the same energy level structure. And then what that means then is it's of course very good as a reference material. Because now if I have a cesium atom and I measure the frequency between these energy levels, everyone who does that measures the same frequency. So, and so what that means then is that the frequencies are tied now to fundamental constants of nature. And what that leads to in the end is accuracy. And this is part of the reason why we refer to instruments like this as quantum technologies, because the quantized energy levels in the atom and the fact that they're related to each other by fundamental constants basically means that the quantum mechanical properties are essential in driving the stability and the performance of the instrument. Okay, so our group, as I said, works mostly with alkali atom vapor cells, although we do have some projects in laser cooling. And basically what this is it's a glass, usually glass cell, or you'll see from sometimes made out of silicon. And it's just sealed and evacuated. And we put a lump of alkali metal inside the glass. Here's actually a picture of a glass ampule that has some rubidium metal inside it. You can see it's metallic in nature. Rubidium melts at about room temperature. And so if you actually take this in your hand and heat it up, it will become liquid. So it looks a little bit like mercury in a mercury thermometer. So what we do is we put a little bit of this alkali metal in the vapor in an evacuated cell, and then of course there's atoms that exist now in the vapor phase. There's a solid or a liquid phase down here, but just like a pot of boiling water, there's also a gas phase that coexists with that solid and liquid phase. And so we have these alkali atoms in the gas phase then that are basically flying around in the vapor cell. Now, if the atoms were just stationary, everything would be great. But in fact, what happens is the atoms are moving at thermal velocities, so typically on the order of a few hundred meters per second, because they're at room temperature. And so what that means is the atoms are continually colliding with the walls of the cell. And every time the atom collides with the walls of the cell, its oscillation, its ticking that is defined by these coherences between the atomic levels is interrupted. And so what this means then is that the atom is continually undergoing disruptions in its oscillation. And that means that the coherence time is on the order of a few microseconds, right? It's basically the length of the cell, say 1 centimeter divided by this velocity. And that means that the atoms are continually colliding and their ticking only lasts for about 3 microseconds. And that means that you don't have a very good clock because the ticking is interrupted continuously. So the solution that was developed back in the 1950s and 60s was to add some kind of an inert gas into the cell with the alkali atoms. And so what you can do then is you can add, for example, neon or argon, or even some molecular species like nitrogen molecules. And if you add the right gas, it turns out that the collisions you basically reduce the mean free path of the alkali atoms down to a few microns. So the alkali atoms then are continually colliding with the buffer gas atoms. And what it does basically is it just lengthens the amount of time between the collisions with the walls. And if you use the right gas, then these collisions with the buffer gas atoms can be very benign. They don't disrupt the spins at all. And it means now that you can get much, much longer coherence times. You can see here, this is 4 orders of magnitude longer. So some of these experiments, actually, if you make a big enough cell, you can actually get coherence times approaching 1 second. And so basically what that does then is it makes the transitions in these atomic species very narrow because the coherence is very low, the decoherence is very low, and that's what makes good instruments. Okay, so first thing I want to talk about is chip scale atomic clocks, and this is work that we did sort of throughout the 2000s. developing very compact clocks. So I've described a little bit about the whole range of atomic clocks, and now I want to tell you how one of these works. So we have a collection of atoms now in a vapor cell with a buffer gas, and these atoms are in some kind of a thermal state, which means that there's some atoms that are in this upper energy level here where the spins are aligned, and there's some atoms in this lower energy level where the spins are misaligned. And so the first thing that happens in an atomic clock is something called optical pumping. Basically what you do is you tune a light source so it's resonant with the transition from one of these ground state levels here up to an excited state. Okay, so this is like an optical field, so it's exciting electronic transitions in atoms. And if you tune this lamp to this light field to the correct wavelength, what will happen is it will excite atoms from this lower ground state level up into the upper level, and then they'll decay back down into both levels. But if they decay back down into the lower level again, they'll get again excited up into the excited state. And since none of the atoms in this upper hyperfine level here interact with the laser field, eventually all the atoms accumulate in this upper energy level, okay, because they're continually getting pumped. And this is a phenomenon called optical pumping. It was developed in the 1950s and 60s, mostly by some scientists in France who got the Nobel Prize for this work in the 1960s. So we do this optical pumping step, and basically what we do then is we put all the atoms now into an energy level where the spins are all now aligned with the electron spin is aligned with the nuclear spin. The next thing we do is this is all done with the vapor cell inside a microwave cavity. And this allows us to inject microwaves into the atoms and excite one of these microwave transitions that I talked about earlier. So in this case, we have this microwave source. It might be, say, at 9.2 gigahertz, which is the transition frequency for cesium atoms. And then when this microwave source is exactly on resonance with the atomic transition, this basically causes coherence in the atomic system. Basically, the atoms are put in a superposition of these two levels. And now what happens is, so when we were in this state here, the atoms were all optically pumped into this level. And so there weren't very many atoms now down here in this lower level. And so the absorption of the light was very small, right? Because there's no atoms undergoing this transition because almost all of them got pumped into this upper level here. But when we apply now the microwave field, now we repopulate this lower level. It drives transitions from this optically pumped level here back down into the level that we depleted. And now the absorption of this light beam goes up. And so if we now monitor the optical power transmitted through the vapor cell, then we can see that when the microwave frequency is off resonance with the atoms, we get a large amount of absorption, and then, a large amount of transmission through the vapor cell. And then when we're on resonance, when we now repump and drive atoms down into its original state here, the transmission drops. And so what we can do then is this as we scan the microwave source, we can see this resonance here, and then we can use a servo system to lock the microwave source up onto the atoms. And that's what generates the atomic clock. So then this microwave source has been stabilized onto the atoms, and because the atoms have these very long coherence times and are not interacting very much with the environment, they stabilize this microwave source, and that's the output of the atomic clock. Now there's one slight modification to this that you can do, and that is instead of putting the atoms in a microwave cavity, you can instead modulate the laser at the transition frequency. So here's an example where we have a laser now. We've replaced the lamp now with a laser, and we are modulating now at, say, 4.6 gigahertz, which basically means that the two first order sidebands of this optical field are separated by 9.2 gigahertz. And these are now interacting with the atoms, right? So you probably know that that if you take a nonlinear resonator, right? Suppose you have a simple harmonic oscillator that has a nonlinearity in it. You've probably studied this in your undergraduate physics classes. That if you drive that with two frequencies, then you can generate an oscillation at the sum or the difference of those frequencies that is essentially established by the nonlinearity. And that's exactly what happens here. Atoms are nonlinear devices. And so if you drive them with two optical frequencies, you can generate a coherence or an oscillation at the difference between those. So this is just basically a simple version of nonlinear optics. So what happens then is we drive these atoms with two frequencies, and we can, through the nonlinearity of the atomic system, establish a coherence or an oscillation between these two ground state levels. And what that does, if we then measure the transmitted power, is we get a similar resonance curve that actually has the opposite sign, but still allows us to lock the microwave source up to the atomic system. And so this is, the nice thing about this is that you don't need a microwave cavity anymore, right? You can just take a laser and you can modulate it. So the goal of our work is to look at the progression of atomic clock technologies. This is what atomic clocks looked like in the 1970s. This is a vapor cell clock. The vapor cell is in this tube here. Here is the quartz oscillators and the frequency multiplication chain. And then there's a bunch of electronics. And you can see over the course of about 35 years, this is kind of a modern clock of about 2005, where everything has gotten smaller. The electronics is a lot smaller. And what our vision here really is to try to make atomic clocks in the way that integrated circuits are made, where you could make all the vapor cells, the lasers, the detectors, and everything in parallel on chips, and basically have now a way of manufacturing these clocks in large numbers on a wafer scale system that could allow for very inexpensive fabrication of clocks. And so, the long-term goal here is to make an atomic clock on every desktop, right? To make it cheap enough that you could put one in every cell phone. And now you could have much better, like, atomically precise timing in a large range of commercial applications. So one of the things that the core ideas is to use silicon micromachining. So you may be familiar with this. This is basically kind of the mechanical equivalent of integrated circuits. So instead of making electronic structures in silicon wafers, what we make is physical structures. And this is a big field that started back in the, 1970s, 1980s. Most airbag accelerometers, like the gyroscope in your cell phone, all use this type of silicon micromachining. And the basic idea is you start with a silicon wafer, you put a photoresist on it, and then you expose the photoresist through some kind of a mask. And then by exposing this photoresist, if you then expose the wafer to some kind of a plasma, after you remove and develop develop and remove this photoresist, then the plasma can etch holes and structures into the silicon wafer. And so these are examples of some kinds of structures that we etched in silicon many years ago, just as kind of a test. So what we did then is we started to make the vapor cells in these atomic clocks out of this etched silicon. So historically, what you did is to use glass blowing techniques to make the vapor cells. So that would involve basically heating up with a propane torch some glass pieces, and then distilling the alkali atoms into the glass tube, and then sealing it off with a propane torch. And so the technique that we developed here is shown here. This was done back in roughly 2003, 2004 timeframe. We etched holes in the silicon wafer using the silicon micromachining. And then we bonded glass onto the top and bottom surfaces and confined the alkali atoms along with our buffer gas inside this hole. So now we can make cells that are on the order of a cubic millimeter in size. And here are some pictures of some of the early, this is one of the first ones we made here. You can see this is about 1 millimeter. And we've made a variety of different ones. This is some with reflective windows in it. Here's a pretty cool cell that was made using kind of chip scale glass blowing techniques, contains rubidium. We've made cells integrated with with photonic structures shown here. We've made arrays of these things. And if you want to learn more about all the processes that we use to make the vapor cells, you can read about them in these papers here. We've also now been able to make large wafers of these. Here is an example of a silicon wafer that has, well, there's 350 holes here showing basically that are potential vapor cells, and we filled them using a new process that I'm not really going to go into. Here you can see rubidium metal that is deposited on the inside of the vapor cell. This is, again, the hole etched in the silicon and glass bonded on the top and bottom. And so we can now make large arrays of these with some reasonable yield. And so now, and this takes on the order of a day or two to make. So by my estimation, the cost of these vapor cells is like less than $1. And in a conventional glass blown vapor cell, it might be a few $100s to make the vapor cell. So it makes the vapor cells essentially free. And so this is, I think, a big step in pushing this toward high manufacturability. And again, this was described in a paper that was written by one of my graduate students, Doug Bopp, a couple of years ago. So if we want to miniaturize vapor cell clocks, I mentioned that, they have, there's a light source, there's an absorption cell and a photodiode, and typically a microwave cavity also. And so the idea with these chip scale clocks is first to remove this lamp. The discharge lamp that is typically used in commercial atomic clocks it's a discharge lamp, right? So you basically put a few megahertz of RF field on this, and it excites the atoms into some excited state, and then they emit light at the right wavelength. But this takes a lot of power, this discharge. And so what we did is to replace this with a diode laser, and I'll tell you a little bit more about this diode laser in a moment. And then we apply, so that's the first step, is to remove the lamp. The next thing is to use, so this microwave cavity is there, but as you probably know, if you take a simple microwave cavity and you reduce the size, there's a cutoff wavelength, and for say a 9 gigahertz cesium transition, that's about a centimeter. So it becomes hard to reduce this this optical cavity or this microwave cavity below 1 centimeter if you want to have it resonant with the 9.2 gigahertz cesium transition. So what we do then is we use this modulation effect that I described a moment ago, where instead of the microwave cavity, we now modulate the diode laser and generate sidebands at the modulation frequency that are used to excite the transition in the atoms. And then finally, we use one of these micro machine vapor cells that I just described as the cavity that contains the rubidium. And with all these things together, this is how you essentially make a very compact atomic clock. So just one note on the lasers. Of course, if you want to make a clock that's very low power, you want to have a laser that is also very low power. Of course, we use semiconductor lasers for this, but most edge-emitting semiconductor lasers have threshold currents that are kind of in the range of a few tens of milliamps, which means that it takes something like 100 milliwatts of electrical power just to turn the laser on and produce coherent light. But there's this new type of laser, well, newish, it was developed in the 1980s, called a vertical cavity surface emitting laser. And this is a laser that is novel because it has light that is emitted in the vertical direction. Most semiconductor lasers, the optical cavity is in the horizontal direction. And it also has very, very high reflectivity mirrors that are made by these Bragg structures. And that means that the threshold currents can be down below 1 milliamp. So here's an example of one of these lasers. This is a commercial version that's packaged inside a can. We buy them typically in die form, and we actually mount them onto a gold-plated substrate that allows us to essentially put current through the laser and basically make the laser laze. The other nice feature of these is that you can modulate them at very high frequencies in the gigahertz range. And so they're ideal for use in these types of clocks. But the main thing is that they have very low threshold currents, and so they can operate on only a few milliwatts of power. So this is the device that we built back in actually late 2003. It was published, you can see here, in 2004. And it basically has a laser on the bottom. It's got a little bit of optics. And then one of these vapor cells sits maybe 3/4 of the way up, and then a photodiode sits on the very top. And here's what the structure looked like. And so we were able to get this working, and we were able to lock up an oscillator to this and make an atomic clock. And over the subsequent 5 or 6 years, companies got involved and developed a commercial version of this. This is a product now that you can buy called a chip scale atomic clock. It's made by, well, Symmetricom was bought recently by Microchip, but they sell these. And you can see the impact, because you have such a small physics package. This is about the size of a grain of rice. And because the laser is such a low power laser, it means that you can build this clock and make an atomic clock that runs on very, very little electrical power. And what I've plotted here is the power consumption of various clocks over the course of about 40 years or so, starting with one of the earliest rack-mounted Hewlett-Packard clocks. And you can see that as these clocks evolved over the course of 40 years, the power consumption went from maybe 40 watts down to 10 watts or something. The chip scale clock runs on 120 milliwatts of power. So it's basically a 30 times reduction in power consumption over any previous atomic clock. And that's what makes it important. With very, very low power, it means that you can use it in applications that, for example, run on batteries. And so now what you have available is atomically precise timing in deployable battery operated systems. All right, I want to turn now to some work on magnetometry. So you can turn a clock into a magnetometer pretty easily. So we mentioned this thing here, this vapor cell clock. So now if you take away the magnetic shield and you put it in a magnetic field, and then you add a polarizer here so that you circularly polarize the light, then essentially you polarize atoms along the direction of the laser beam. And then if you drive this with an RF coil instead of a microwave cavity, then what you do is you essentially drive the precession, you polarize the spins using the laser, and then you drive the precession of those spins about the magnetic field. And that precession frequency is the Larmor frequency, which is related to the applied magnetic field by these fundamental constants. So if you measure the Larmor frequency, then you can deduce from that what the magnetic field is that the magnetometer is sitting in. And so we've built very similar versions here. This is, again, a chip scale version. It's very similar to the clock. There's a laser down at the bottom. There's a vapor cell part of the way up. You can actually see the magnetic field coils here that drive the spin precession. And when we locked all this up, we were able to make a magnetometer with a sensitivity of about 6 picotesla per root hertz, which is pretty good in the magnetometer field. And we measured the bandwidth to be about 1 kilohertz in this case. We've also been able to make fiber optically coupled versions of this. So in this version here, the laser is sort of on the chip. In this version, what we did is to couple light to the vapor cell using optical fibers. And so now we can get the laser, we can put the laser in some location different from the vapor cell. And so here is basically the light. The vapor cell here is suspended on these Kapton structures, and the light comes in and is directed downwards through the vapor cell, and we can do our magnetometry there. We have to heat the vapor cells up to about 100 degrees C to make them work optimally. And so one of the things that we don't want to do, of course, is to put any kind of electrical currents near the vapor cell. And so this was a design where to heat the vapor cell, what we did is we put colored glass on the top and bottom, and we sent light in that would be absorbed this was at, I think, 980 nanometers, that was absorbed by this colored glass. And so as the glass absorbed the light, it heated the cell up, and we could make it work that way. So here's a picture of one of these magnetometers. And you can see here, this was working with a little bit different regime, but we were able to get down to 20 femtotesla per root hertz here, which it turns out is quite competitive with the best magnetic sensors, which are based on superconducting circuits, superconducting quantum interference devices. And so now we have a device that is very small and low power, but that can achieve sensitivities that are comparable to cryogenic systems, which are of course far more complicated to operate. And so over the course of many years, we built these back in again, late 2000s, early 2010s. There are now a number of companies that are manufacturing some version of this, and they're actually being used now for measuring magnetic fields from the human brain. Here is a system that is being developed where there are these magnetic sensors here, and by measuring the magnetic fields from the brain, you can get some information about the neural currents, and in fact, there's a potential clinical application here for diagnosis and treatment of epilepsy, because you can get information about where the epileptic activity is situated in a patient with epilepsy, and that helps, for example, if there needs to be a surgery or some other kind of intervention to help the patient. So this is now kind of moving forward and is kind of a bit of a hot field right now. We've put these magnetometers on rockets, put them in space. This is a picture of a sounding rocket that was launched about 4 or 5 years ago. It was launched basically from this island in Norway, and it went up to, you can see this is a scale of the height here. It went up to about 700 or 800 kilometers at its highest point, and then crashed down in the Barents Sea. We actually did recover the magnetometer. And this is data from the magnetometers. Don't worry about all this text here, but this is basically the magnetic field that it measured as the rocket flight happened. And this is really just a demonstration mission to show that we can put these magnetometers in space. And we're now working to try to develop future sensors for future space missions, so potentially for Earth science or for other planets. Okay, I'd like to turn now in the last little bit to work that we've been doing, kind of extending this to kind of a programmatic vision that we call NIST on a chip. And the idea with NIST on a chip is to say, okay, so these are, on the top here are various types of primary standards that are used at NIST to measure various things. So this is an optical clock that actually is a wavelength reference. Also, sorry, this is a fountain clock that is it's a clock, so it measures time. This is an advanced wavelength reference that essentially measures length. This is something called a watt balance that actually is the way now that mass is measured. The kilogram is defined in terms of this watt balance here. And then this here is a voltage reference that's based on a cryogenic Josephson junction device. And so these are all, you can see, fairly large, sort of laboratory scale instruments. And so what we're doing at NIST right now is to think about whether we could convert some or any of these into something that could be deployed on a chip, right? So imagine you had a chip that was kind of, instead of doing a calculation or something, what it would do is it would provide an SI traceable reference for whatever unit you happen to want, right? So I've shown one here with lots of different outputs here, but whatever you want. So suppose you just wanted to measure length, then this chip could be made potentially at low cost that would provide length as an output. And so now you can imagine, building these into instruments. So imagine every optical spectrum analyzer had one of these chips in it that would calibrate the wavelength of this optical spectrum analyzer to the SI for the lifetime of the instrument. So that's one possibility. We think about voltmeters and temperature sensors and all kinds of things. And this is important. So this is important at NIST because we spend a lot of time calibrating things, right? And if we can build inexpensive chips that could allow users to calibrate things themselves, then it makes the whole calibration process much, much better and much, much more efficient. So what's in these devices? So we're building these using photonic systems. And the basic design is kind of shown here, where we have an integrated photonics layer that delivers the light to the right location. And then we have this layer of atomic vapor cells where we can, where this is the SI traceable quantum reference. And by interacting, having these interact, we can build highly integrated and highly manufacturable systems that can realize, for example, length standards. I think I'm going to skip this, but this is one that we made a few years ago. This is basically, the black thing here is a photonics chip. It's basically a silicon substrate with a silicon nitride waveguide on it. And the silicon nitride waveguide is maybe, I don't know, something like 20 nanometers high and a few hundred nanometers across. It guides light just like an optical fiber does on the chip. And so we have light that is off the chip that comes on through optical fibers, and then it goes into this waveguide, and then it is coupled up through one of these vapor cells, and then we can measure spectroscopically the wavelength of the laser by scanning the laser wavelength over these atomic transitions. And here are examples of transitions that we measure in this system. That we can measure Doppler free lines using saturated absorption spectroscopy, and we can stabilize lasers. Here's an example where the blue is the unstabilized laser, and then the red one is the stability of the stabilized laser. And so you can see we can get factor of 100 or something like that, better stability. We can also get good accuracy out of it. And so we're now working with a couple of companies to try to commercialize this. You know, it basically means that it's a wavelength reference, right? It provides light that is where the wavelength is known to about a part in 10 to the 9, and that means that that you can measure length. We're also developing optical clocks now. So most of what I've talked about in the past are microwave clocks. You may know that in the early 2000s, there was this wonderful thing that was developed called the optical frequency cone. And the optical frequency cone basically allows you to take an optical reference like this, a laser, and divide it down into the microwave domain to make a clock. And this was revolutionary for atomic timing. These two gentlemen, Jen Hall and Ted Hensch, got the Nobel Prize in 2005 for their work developing optical clocks and frequency cones. And you can see here, this is a plot of the timing uncertainty essentially over many decades, starting in the 1950s. And the blue lines are the microwave clocks, and the red line is optical clocks. And you can see right around when this frequency cone was invented in roughly the mid 1990s, these clocks got much better. So we're developing optical clocks also, but chip scale versions. So this particular one here is again implemented in one of our microfabricated vapor cells, and it's actually based on a 2-photon transition in rubidium. It turns out that 2 778 nanometer photons can excite the rubidium atoms into a higher lying D state, and this state then decays through a cascade emitting light at 420 nanometers. And so if we take a laser and we scan the wavelength, we send it through the vapor cell, and we scan the wavelength, we get resonant transitions or a spectrum that looks like this. These are different hyperfine levels in the excited state. And these are very narrow. The line width of this is on the order of 300 kilohertz. And that means we can make very good wavelength references. Here's an example of one where we basically have stability now of about 2 times 10 to the minus 12 at 1 second, and integrating down into the 10 to the minus 14s. And so this is a very good clock. It's much better than the microwave clocks because the optical frequency is a lot higher, and that means the Q factor is a lot higher also. So we've been able to integrate this with, so we need a comb with this, right? This is at an optical frequency. And we've been able to integrate this with micro-resonator frequency combs that essentially allow us to take this optical frequency and divide it down to this 22 gigahertz clock output. And and these are all based on whispering gallery mode optical confinement in very small microscopic or milloscopic optical resonators. Basically this is the chip scale clock, and when we built this entire system here with optical frequency divided down, we got this stability here, which is, you can see, about a factor of 30 or 40 better than a chip scale clock. And in fact, we've even gone further. If we use very low noise lasers, we're able to get stabilities down in the range of about 10 to the minus 13 at 1 second, which is now about 3 orders of magnitude better than a chip scale clock can do. And so this is a very promising technology for advanced chip scale atomic timing. The stabilities are much better, even into the 10 to the minus 15 range. And so we're, again, working with some companies to try to commercialize this and make the next generation of chip scale clocks. I think I'll skip this here. The newest thing we have that is actually not even published yet, but so that you're one of the first people to hear about this, is we're now making chip scale atomic beam clocks. So atomic beam clocks are based on a thermal beam of atoms that basically fly down along a tube like this. This is a NIST-7 that was the primary standard for the United States in the 1990s. And there are commercial versions. This is actually one of the very first ones that was built. And there are commercial versions of this here that you can buy. This is called a 5071 beam clock, and it's a real workhorse for telecommunication systems. And the reason we want to look at cesium beam clocks is that because the atoms are flying just ballistically down a tube, then they don't interact with anything, either a buffer gas or the walls of the tube. And so that means that you can get very good accuracy out of them. And so here, for example, is chip scale clocks and rubidium clocks. This is the timing error of 1 day as a function of the power. And you can see that you can get something like 100 microseconds of timing with vapor cell clocks, but with cesium beam clocks you can get sub-microsecond timing. So this is a compelling technology, and so we just got some recent results on this. So this is a picture of our chip scale beam clock here. This is the beam tube in the center region here. It's about maybe 1.5 centimeters long. This is all fabricated using the same silicon and glass fabrication procedures that we use to make our vapor cells. But what we do now is we put the rubidium in a chamber at one end of the tube. And then we have these very, very thin channels that connect this source region, this rubidium source region, with the tube. And so here we have these rubidium pills to create the rubidium. There's these silicon channels. And now we get this rubidium atomic beam that comes down here that we can use for spectroscopy and use to make a clock out of. We have a couple other things here. There are these getters here that are passive getters that pump away most of the gases. And then we also have to, once the rubidium has come out here and goes through the tube, goes down the tube, it starts to stick on the walls. And so we don't want that. We don't want to have the vapor in here. So we put graphite in the beam tube to pump away all the rubidium and have a nice clean beam. And so here's a picture actually of some of these very, very thin channels that we use to create our collimated beam of rubidium atoms from this source region here. This is a bit of a busy plot, but this is just basic spectroscopy showing that we do indeed have an atomic beam. The purple trace is the one that's most important here. This is just if we scan a laser looking perpendicularly down into this vapor cell. Typically, you get a Doppler broaden curve, and this purple line here shows a clear narrowing of the Doppler peaks that is associated with an atomic beam. And we can measure the flux of about 10 to the 12 atoms per second, and we can also measure the transverse temperature, which is important. And so we've done a lot of characterization of this device. But the most important thing is we can now do a 2-zone Ramsey experiment where we send, again, a modulated laser. This is a coherent population trapping or EIT type clock. And this was actually developed back in the 1980s by Shaul Ezekiel and others at MIT. And so we send this laser down here, and then we measure the fluorescence. And this is basically the fluorescence that we get as we detune this modulation frequency around 6.8 gigahertz. And you can see we see a clear Ramsey fringe here that is indicative that we have a clock. And so this is the very first data. We're just writing up a paper on this, showing this Ramsey fringe from this chip scale beam clock. And we still have to work to, we've locked up an oscillator, but it's not very stable because the clock isn't working very well at the moment. Signal to noise is not so good. But we're working on this now to improve the performance. And eventually we think that this will be a nice complement to conventional chip scale clocks because it has intrinsic accuracy, whereas the conventional vapor cell chip scale clocks don't have that. So this is part of our NIST on a chip kind of vision here, is to create accurate timing on a chip using this beam clock approach. And I'm going to skip the strontium vapor cell stuff. I'm just going to mention this kind of cool project that one of my postdocs did a few years ago. He showed up in our group. He's from Israel, and he showed up and he said, I want to make this cool thing. And he told me about it, and I was like, yeah, this is pretty cool. So what it is basically, what he did is he took a wafer of silicon and he etched slots in the silicon, spaced by, I don't know, a few tens of microns. And so this is a diffraction grating, right? If you shine light on it, the light will interfere in a way that you'll get diffraction that happens at certain angles. And then what he did is he used our vapor cell filling technology to essentially fill all of these little gaps here with rubidium atoms. So now what this is now is it's diffraction grating, but it has some optical activity that is related to the rubidium. So depending on how you tune your laser, the rubidium atoms generate some phase shift in these slots here. And instead of getting a clean diffraction pattern, you get a diffraction that depends on the wavelength. And so here is some data here showing that at very low temperatures, you get the standard absorption. But when you get to high temperatures, you actually get all these interference fringes that are coming from the phase shifts induced on the light by these rubidium atoms. And he made a lot of kind of interesting, this is an example of, a lot of interesting things. This is an example of some Fresnel lens that basically focuses light down. But again, it focuses light based on the frequency of the light because of the resonances of the rubidium atoms here. We don't know exactly what this would be used for at the moment, but it's kind of a cool idea. That's something cool that he made. And maybe it could be a wavelength reference that's highly tunable. But it was a fun little project that we did. So I'm gonna stop here just to say that, you know, we're, as I mentioned at the beginning, looking at precision spectroscopy. We're integrating photonics and also silicon micromachining, and we're making a variety of different clocks, magnetometers, optical clocks now, and some kind of novel things also. So with that, I want to finish. I just want to acknowledge my research group at the moment. Matt Humman is the project leader at NIST. He's a NIST staff member, and he's been developing this 2-photon clock. William McGeehee is a new staff member at NIST, and he's been developing the chip scale beam clock along with some graduate students. And then Susan Shima is a technician in our group, and she does a lot of the silicon fabrication. And then all the people who really contributed to this work on the early work in chip scale clocks and chip scale magnetometers, including, as I was talking with you earlier, Eduardo, Ricardo Jimenez Martinez, who was actually from Mexico and came and worked with us for a number of years and made a lot of important advances in our magnetometry program. And also a lot of collaborators from other research institutions that have helped us in this work a lot. So with that, I'm happy to take any questions that you have.
Thank you very much. That's a really exciting talk. It was also very clear. So I invite anybody that has a question to post it on the YouTube channel. So while people start putting questions in there, I may start with one. So all of this work is done with rubidium. I saw that you probably skipped some slides on other atoms. But what would be the reasons to abandon rubidium and not use it?
Yeah. So so this is some work that we've been doing on strontium. So rubidium is a workhorse atom for many types of instruments, right? The cesium is actually the definition. It is the atom on which the second is defined right now. And rubidium atoms are very easy to work with because they have very high vapor pressures and they have a very simple electronic structure because they only have one valence electron. But other types of atoms, for example, alkaline earth atoms that have 2 valence electrons, are emerging as new sort of quantum systems. Most importantly for atomic clocks, the best atomic clocks now are based on strontium or ytterbium. And so we've been making vapor cells with these strontium atoms. This is a picture of some of these vapor cells here. This is a lump of strontium, and we put special coatings, sapphire coatings on the inside of the vapor cell to protect the glass from the sapphire. And we can measure Doppler free lines in strontium. And so ultimately what we'd like to do with these types of vapor cells is we potentially can have much narrower lines. For example, strontium has a transition at 689 nanometers that's only 7 kilohertz wide. And if you can get down to this, so for example, our 2-photon transition in rubidium is 300 kilohertz. So if we could get down to this narrow transitions, then we could access make much better clocks. And so there's different types of, so this is an example of another type of atom. We're also looking now a little bit into Rydberg atoms. So in these vapor cells with rubidium or cesium, you can excite the electron up into a very, very high-lying orbital, and that has very high sensitivity, for example, to electric fields. And so but that's also with rubidium or cesium. So you kind of choose your atom depending on what you want to do with it, I would say. So yeah.
Okay, thank you very much. And another question, I saw in your slides some of the light at 780, but I think I also saw some light at 1560 with the doubling frequency, taking advantage of the telecom in technology. What would be your take on what do you prefer?
So we've done both, right? So let's see, where is that? So the transition in rubidium that we're working with is at 778 nanometers. And we can generate that in 2 different ways. We can either start with a laser at 778 nanometers and interrogate the atoms, or we can start with 1.556 microns and frequency double that in a nonlinear frequency doubling crystal. And that generates light at 778 nanometers. And the advantage of going to 1.5 microns is that there's generally better laser technology there. And that's because telecommunications uses that frequency band. And so there's been a lot of work developing lasers at that wavelength. One of the important things that limits this stability is actually the line width of the laser. It's the frequency noise on the laser. And so if we can get better lasers, we can make better optical standards. And that's exactly what we did actually in this experiment here. We switched from a DBR laser, which has a line width of about 1 megahertz, to an extended cavity diode laser, which has a line width of about 10 kilohertz. And it turns out that there are 1.5 micron lasers that are even narrower than this. And so so in some experiments that we do, we actually use the 1.5 micron laser because it has a narrower line width, and we frequency double that, and then we use that to interrogate the atoms, and that tends to work better. My suspicion is that in the end, for the best performance, we will end up with that kind of system with the 1.5 micron source. We're looking into things like lasers based on stimulated Brillouin scattering, SDS lasers are called. These have very, very narrow line widths, sort of Hertz level line widths. And so if we can get to those very narrow line widths, it means that the clock here stability can be much better, maybe down into the 10 to the minus 14s. So it's really a question of what technology is available, what line width's available, and so that's the reason we choose that.
Okay. So Alex Sandoval asks, in addition to the limitations in electronics, is there any limitation in fundamental physics that presents a problem in the shrinkage of these devices?
Well, yeah, so this kind of gets back to, I'm not sure it's fundamental physics, but gets back to this idea of vapor cells, right? And so there's a basic kind of fundamental scaling, at least with microwave clocks and with magnetometers, where the smaller you make the vapor cell, the worse the clock is. Okay, so there's a very general trend that larger, bigger clocks are better than smaller clocks, and part of that is the electronics. You're right, but part of it really has to do with this collisional decoherence, right? So if I have a big vapor cell and I put a buffer gas in it, then it means that the alkali atoms are basically diffusing in this vapor cell, right? And so the larger the vapor cell is, the longer the relaxation time. So here the T2 is proportional to the length, the size of the vapor cell. And so as you make the vapor cell smaller, there are more frequent collisions of the alkali atoms with the cell walls, just because the diffusion is the same and the walls are closer, right? And that makes the relaxation time shorter, and it makes the resonances broader and the clock worse. So there is this fairly fundamental scaling between, at least for this type of clock, between size and performance. That said, when you look at the chip scale clock, right, the vapor cell is only 1 cubic millimeter, and the entire clock is about 10 cubic centimeters, right? So most of that's electronics and the packaging and all the things around it. But in the end, if you want to get to low power, you do have to have small vapor cells, right? And so I would say that the more important parameter for chip scale clocks is not the size, it's the power consumption. And that's what really distinguishes it most from other types of atomic clocks, because it means you can operate them on a battery. So even if the clock was larger and had the same power consumption, it would still be more or less as useful as a smaller version. And it's really the millimeter scale vapor cell that allows you to get to the low power consumption.
I see. So Jorge Arola is asking, can you comment a little bit about the stage between the research and the potential commercialization of the equipment developed in the lab? Who takes charge of this part of the job?
It's a very, very interesting and a very good question, right? This is we refer to it as technology transfer here in the United States, and the basic idea is, there's lots of research that is done in universities and government labs, and often, the researchers, their main goal is to publish papers, right, in journals. And they kind of, okay, so you do a bunch of work, you publish your paper, and then you move on to the next science project. The industry people, of course, want to have new technologies coming into their companies, but often they're not technologically advanced enough that they can easily adopt something that comes out of a university or a national lab like NIST. And our group has really been kind of at the forefront of developing instruments that really could be adopted by industry fairly easily. So we have two big successes. The chip scale clock is a commercial product, and the chip scale magnetometer is a commercial product now. And there's several others we have ongoing that are getting there. Really what it takes, I would say, is willingness on the part of the researchers to engage with industry and to spend time doing that. So like our group, we work with a lot of companies, and we spend a lot of time, I don't know, a third or quarter of our time trying to explain what we're doing to companies, address problems that they have, reduce the risk for them for certain issues. And then it also takes money, right? Most of these companies, they're not going to adopt something like some crazy chip scale beam clock thing unless they have funding to do it. They just don't have the internal resources. And so typically the way that works in the United States is that there are government funding agencies that provide funding to companies, and often to us also as a national lab, where we can work together to help the company understand, and the company can then put people on this and build things. And the hope is that it eventually, gets to be a product that is also driven by the market, right? I mean, you want to have this thing useful. And so yeah, it does happen, but not always. Sometimes there isn't funding available to commercialize something. Sometimes the things that we develop don't have a clear enough application in the real world to really motivate a company to commercialize it. And so it's all a bit complicated and messy. And what we do is we don't have really a particularly good known algorithm for doing it. We just try to get our stuff out there, talk to people as much as we can, and work as hard as we can to get this to work. So it's an interesting question. It does happen though. And it's, for me anyway, it's part of the reason I do my job is because I love seeing technologies that we develop actually used in helping people, you know. So.
Great. So Mario Cervantes is asking, have your team been working on the shrinkage of atomic gravitors? Because it seems that you have a lot of the main components already.
Yeah, so we have about a third of our group right now is developing cold atom instruments. And the goal of that, again, is to take, you know, laser cooling is a very powerful technique. It clearly enables, you know, all of the best atomic clocks over the last 20 or 30 years. And it also enables things like gravimeters and gyros and other measurement instruments. And we've been doing this for 15 years or something like that. I will say it's much harder to do than vapor cells. Vapor cells are such a simple system that when we can use them, we do. And there has been probably $200 million over the last 15 years in the United States invested in trying to make compact cold atom systems, and nobody has really succeeded. So we have work going on in this direction right now. You know, we're trying to make, for example, a chip scale cold atom platform, right, where we could take, you know, one of these MEMS vapor cells and try to generate cold atoms in it. The problem there is that it's really hard to get a 10 to the minus 9 torr vacuum without an ion pump or a turbo pump or something, right? And those are big, and nobody knows how to make small versions of those. So the vacuum is a key thing here if you want to make things miniaturized. And so, you know, the things that we make are sort of like conventional systems, sort of this size, whatever, you know, physics packages. And I would say that there's still a lot of work to be done in that area. I think it will happen eventually, but we have to solve these pumping problems, and they're not easy problems to solve. So anyway, I'm sort of lukewarm on chip scale cold atom systems at the moment, really because of the complexity. I think that the systems that we're going to get are going to be filing cabinet sized, or maybe rack mount sized things, but they're not really going to be chip scale until we can solve these issues with regard to getting good vacuums on a chip.
Okay. What is the final size of the optical clock that you were developing? Is it about the same size as the microwave?
No, it's going to be bigger than that. So what happened with this project basically is we were trying to develop this 2-photon clock. So this is the version that we wanted to build, right? And we actually did build this, you know, and so, but the problem is it looks nice and simple here on this slide. But when you actually look at it, this was on, you know, 3 different optical tables in 2 laboratories with 4 racks of electronics to run it, and several laser systems off to the side. And what we found as part of this work is that the microresonator combs here are not really ready. They were not able to make good combs at low enough power. The optical part worked okay, I would say, but it's still pretty big, right? I mean, this is the module that we made here. It could be made smaller, but this is kind of what we were working with. And so going forward from here, we're now working with a couple of companies to commercialize this, but the idea is to get rid of the microresonator combs and just use fiber combs. So that means that you know it's going to be 10 or 30 watts of power for sure. The goal here was 100 milliwatts or 250 milliwatts of power. That was the goal here, and to have something that was, you know, small and compact. So this potentially could do that, but it's the photonics part is just too hard at the moment. So my guess is that what this will turn into in the end, I think there will be a product that will come out of this. It's a good clock, but it's going to be a rack mount thing, but it will compete with a hydrogen maser in terms of market. So what we want to try to develop here is hydrogen maser performance that can be a factor of 10 lower cost and a factor of 10 smaller size.
I see.
It's not going to be chip scale.
Okay, I think I don't see more questions on the YouTube. Perhaps one more last question from my side. When you stack all the things on top of each other, how do you make the alignment of the pieces with respect to each other? Is that a big issue?
In the chip scale clock?
Yeah.
Yeah, it's actually not that big an issue. So, you know, in this device here, it's just, these are just all glued together. And this was literally made using like tweezers. We mounted the laser on the bottom here, and then we built this little optics assembly with glue, and then we glued it onto the base plate, and then we mounted the vapor cell. And you can see we did some absolutely crazy things here. So this was before we got very good at our photodiodes. And what we actually did here is the photodiode is mounted onto a little gold pad, but the gold pad is actually on the underside of this piece of glass here, right? And so the wire bond actually goes up and it goes underneath. And so what we would do is before we mounted the photodiode, we would bond a gold wire onto it and then have the gold wire hanging loose. And then we'd flip it over and glue it onto this vapor cell, and then somehow, you know, get the gold wire bonded down onto this thing. And you can see and they would break all the time, right? And so we'd be messing around, the gold wire would break, and then we'd have to get some, like a pin and get some glue underneath here and glue the gold wire back onto the pad. It was just kind of, it was kind of craziness for a long time. The companies do this way better. They have it all sorted out and stuff like that. But the alignment doesn't really, you know, this is just literally aligned with a pair of tweezers. Okay. Because the laser beam is coming up here and it's spreading out as it comes up, and it's probably about, I don't know, 1 millimeter in size when it gets to the vapor cell. So as long as your vapor cell is close, it works fine.
Works fine.
Yeah.
I see.
So the alignment is not hard.
Okay. Well, I think there are no more questions, so I would like to thank you again for this fantastic talk. It was very instructive for all of us, and for accepting our invitation. It was a pleasure to have you here.
Very welcome, and a very pleasure for me also. So.